In this video, I'll describe how to use the chi-square distribution for research questions related to homogeneity. Over the past decade, there have been numerous studies that have suggested a link between red meat consumption and cancer. So, researchers are interested in determining how much red meat people consume and how this varies from place to place. First, researchers wondered whether people in the US, the UK, and Germany eat the same amount of red meat. So they wanted to compare three populations. They surveyed 202 people from the US, 138 from the UK, and 120 from Germany, and they asked them to describe the frequency at which they ate a serving of red meat. So this is a categorical variable, and they counted the responses in each category. Now, the null hypothesis is that these three countries all have the same distribution. In order for us to more clearly articulate this, we need to specify what all of the parameters are. I'd like you to pause the video and think about what the parameters are. It turns out that there will be 15 parameters. One parameter is the percent of people in the US who never eat red meat, which we'll represent as pi sub US, never. Another parameter is the percent of people in the US who eat red meat a few times a month, which we'll write as pi sub US, month. So there would be one parameter for each entry in the table, a total of 15 parameters. Now, for our null hypothesis, we need to capture the idea that the countries all have the same distribution. So, for example, the percentage of people in each country who never eat meat should all be equal to each other. And what should these percentages all be equal to? Well, if we look at the totals for each country, overall, 71 out of the 460 people never ate meat. So if the three countries had the same distribution, then the percentages should all be equal to 71 out of 460. And the next parameters should all be equal to 16 out of 460. And the next should all equal 106 out of 460. Then 214 out of 460. And 53 out of 460. And this set of equalities, altogether, is the null hypothesis. After creating the null hypothesis, we use it to compute the expected values, the number of people in each cell of the table, assuming the null hypothesis is true. I'll make some space to compute these values. Now, for the number of people in the US who never eat meat, we'd take 71 460ths of the 202 people who never eat meat. So we'd multiply these to get the expected value, which would be 31.18. Then for the UK, we'd take 71 460ths of 138 to get 21.3. And we'd keep on multiplying the proportion for the row by the number of people in the column. So now we have our observed values and expected values, and we need to compute a statistic that lets us summarize the difference between the observed and expected values using a single number. We do this using the chi-square statistic. So first we'd take the first observed value, subtract the corresponding expected value, square the difference, and divide by the expected value. Then we'd repeat this process for the next pair of observed and expected values, and add. Then we'd repeat this for the next pair of observed and expected values, and continue this process. After doing all this, we'd get 8.6. And this number summarizes the difference between the observed and expected values. Finally, we need to determine whether this statistic is strong evidence against the null hypothesis. Since our expected counts are each roughly at least 5, it will be okay for us to look at a chi-square sampling distribution. But first, we need to know which chi-square distribution. That is, we need to compute the degrees of freedom. In our observed values, the totals for each row and column are fixed. For example, in the US, there have to be 202 people, and there have to be a total of 53 people who ate a serving of meat more than once a day. So, the value in this cell can vary, as can the value in this cell. But since the total in the row has to add to 71, the value in this cell would be fixed. And this is true of each of the first 4 rows in the table. Since the first column has to add to 202, after the first 4 cells in the column can vary, the value of the 5th cell is fixed, as is the case for these other 2 cells. So overall, there are 8 cells whose values can vary, so there are 8 degrees of freedom. So we can look at a chi-square distribution with 8 degrees of freedom that is created from a null model. Then we'd look at the chi-square statistic and compute the probability of getting this statistic. In this case, this probability, the p-value, is 37.7%. What this means is that if these countries have the same distribution, and we took many samples of 202, 138, and 120 people, we would get a chi-square statistic of 8.6 or larger in 37.7% of these samples. So this is not evidence against our null hypothesis that the countries have the same distribution. Now let's summarize what we've done here. So in this video, we did a type of analysis called chi-square for homogeneity. It is used for research questions that ask whether multiple populations have the same distribution of counts. In our example, our 3 populations were people in the US, the UK, and Germany. Our null hypothesis was that the distributions were identical. We used this hypothesis to compute expected values and a chi-square statistic. Then we determined the degrees of freedom by recognizing that 1 row and 1 column of values would be fixed and the others could all vary. Finally, we compared the statistic with a chi-square distribution to compute our p-value and make a conclusion about our null hypothesis.